Look at this photograph of clear plastic bottles rolling down an industrial conveyor belt. The invisible foundation making these bottles and the antifreeze in your car possible is a chemical called ethylene glycol. Making enough of this chemical to supply the world requires massive industrial factories. At the heart of these factories is a liquid helper called a catalyst. This liquid constantly loops through the system, speeding up the reactions to keep production moving. This liquid helper is incredibly expensive. Because it circulates endlessly through miles of factory pipes, it has to be kept absolutely pristine. Even a tiny impurity can cause a massive headache. The profitability and survival of the entire plant rely on keeping this continuous loop of catalyst completely free of contamination. To keep production running smoothly, engineers add helpful chemicals early in the process, but these additives carry dark impurities called organic chlorides. When these impurities interact with the looping catalyst, a reaction triggers. They break apart and reform into jagged crystalline salts. Acting like sandpaper and acid, they cause a type of corrosive cracking that eats away at the smooth metal walls. Over time, these solid particles accumulate. If left unchecked, they will literally eat right through the thick steel infrastructure of the factory. A microscopic pinch of salt has the power to destroy a multi-million-dollar facility from the inside out. The engineers had to find a way to stop it. For years, the industry relied on a brute force method to deal with this salt buildup. They called it catalyst bleeding. Because the corrosive salt was trapped inside the valuable catalyst fluid, engineers had to physically open a valve and dump a portion of that contaminated liquid entirely out of the system. It was like throwing away buckets of liquid gold just to get rid of a few pebbles of salt. This method wasted highly expensive materials and demanded constant maintenance shutdowns. It was a massive drain on the plant's bottom line. This diagram shows the actual engineering flow of a chemical plant. To understand how modern engineers fix the problem, we need to trace the path through this system and find exactly where the salt hides. We can simplify this into 3 distinct zones, connected by a continuous pipeline. In the first zone, base ingredients combine. The stream flows into the second zone, where water is added to create ethylene glycol. But hiding inside is our salt saboteur. This photo shows towering industrial columns. On our map, this represents the third zone, the dehydration column. It is a giant, low-pressure boiling tower designed to safely cook off all the excess water from the previous step. Instead of bleeding the precious catalyst out of the system, modern engineers realized they could use this massive boiling tower as the perfect trap to catch the saboteur. To set the trap, engineers intentionally allow a tiny, calculated amount of one specific molecule to remain in the mix as it enters the boiling heat of the dehydration column. In the intense heat of the dehydrator, this molecule crashes directly into the solid corrosive salt. The impact forces the dangerous solid salt to break apart. It chemically transforms into a brand new substance, a harmless liquid byproduct. Unlike the sharp salt crystals, this new substance is not a corrosive solid. It is now just a liquid that dissolves easily into the surrounding water. The engineers didn't try to physically filter the hardware-destroying solid out of the pipes. They used chemistry to force it to melt into a liquid. This newly formed liquid byproduct seamlessly dissolves into the wastewater that is already boiling off inside the column. The former saboteur is now safely flushed out of the factory through standard wastewater drains, completely harmless to the metal pipes. Meanwhile, the pure, completely salt-free, highly valuable catalyst flows out the bottom of the column, safely recycling back to the start of the factory loop. By understanding the chemistry of the saboteur, engineers eliminated the wasteful catalyst bleed and saved millions in hardware. They replaced a clumsy brute force process with a precise chemical solution.